Hi everyone, I'm Zaidrawi from BP. Welcome to this IChemE webinar. This is a joint one between computer-aided process engineering and also the Process Management and Control Special Interest Group. So as I said, I'm Zaidrawi from BP, and also we have another presenter, organizer is Dr. Yin Ling from Curtin University. So delighted to have so many people attending this webinar. This has got to be a record, I think. So this one is on generative AI, artificial intelligence in chemical process engineering. It's envisaged that generative artificial intelligence will have a huge impact on chemical process engineering. Gen AI has gained immense traction across diverse sectors, exemplified by remarkable achievements such as ChatGPT's language generation and GitHub Copilot's code generation. Gen AI also holds immense potential to reshape chemical process engineering by offering advanced data handling, modeling, and decision support capabilities, ultimately driving innovation and efficiency in the industry. However, there are only limited applications in chemical engineering so far. Promising applications are proposed for Gen AI in process engineering, including auto-completion of flowsheets, auto-correction of engineering documents, P&ID generation, and AI-assisted HAZOPs. And it's felt there is a need to conduct more research and development in three main areas to ultimately develop useful Gen AI tools in this domain: data, information representation, and model architectures, including mechanistic information. So our speaker is Artur Schweidtmann. He's a professor at TU Delft. In fact, he's a tenure-track assistant professor for chemical engineering and director of the Process Intelligence Research Lab. His research focuses on the combination of artificial intelligence and chemical engineering, of course, and he received his Master of Science from RWTH Aachen University in 2017 and defended his PhD in 2021, both in chemical engineering. During his studies, he spent the academic year 2013-2014 at Carnegie Mellon University as a visiting student via the DARD ISAT program, and he performed his master's thesis at the University of Cambridge. So I'll hand over to Artur. Please pop your questions into the question pane as you go, and we'll endeavour to answer as many as possible at the end. But with such a huge attendance, we may have to take some offline. Artur, over to you.
Perfect. Yeah, thanks a lot for your kind introduction. Thank you all for coming. It's a great pleasure to give this webinar. And it's particularly a great pleasure to have so many people online here. So the talk of my webinar today will be generative artificial intelligence in chemical process engineering. And I think I don't need a long introduction about generative AI. So generative AI is now, everywhere. Essentially, we're starting to see more and more applications in different domains. And some of the examples are, for example, in natural language generation. For example, ChatGPT, many of you know. Also, generative AI has been able to generate images. There's, for example, the DALL-E model. Very recently, like a few days ago, there was a new release of generative AI generating videos as well. And a bit closer to our domain, there's also multiple examples where generative AI algorithms are generating molecules, in particular molecules with specific properties or functions. However, in my talk today, I would like to talk about generative AI in the process systems engineering domain. And here we see, very limited applications so far. So the questions I would like to answer is, first of all, is it feasible to develop a generative AI for us, for the process systems engineering domain? If we develop it, how would it look like? And what does it take to actually develop it and deploy it in industry? And what I would like to do is I would like to guide my whole presentation today through three exciting generative AI applications. And these three applications will be inspired by existing generative AI applications in other domains. So let's start with these existing applications. The first one is GitHub Copilot. GitHub Copilot is a platform that is automatically completing programming or software code for you. So this is quite established already and used by developers throughout the world. So what is happening if you develop a computer code, if you write your own software, and you use something like GitHub Copilot, what it does, it will basically auto-suggest completions of your code. So for example, you can start by writing a comment. I would like to implement a function that is doing X, Y, Z. and then GitHub Copilot will automatically suggest an implementation of that function. And this is, quite commonly used. It's a productivity boost. So for those of you who are coding, who are not trying it yet, it's really worth trying. The second example of very successful generative AI in other domains is machine translation, in particular applications like DeepL or Google Translate. So these applications are able to generate language from or text from one language to another language. For example, I'm living in the Netherlands now. I need to translate a lot of emails from English to Dutch, or German to English, or German to Dutch. And using these online tools like DeepL, this has become much easier than it used to be, right? So the accuracy of these tools is extremely high nowadays. And I can even, translate to Chinese, Japanese, stuff that has not been possible a few years ago. And the third generative AI application I will mention here is autocorrection of text, and there in particular Grammarly. So Grammarly is an autocorrection tool that is very similar to the autocorrection that you might know from Word, but better. So this goes significantly beyond checking each individual word and checking if that's a correct spelling, if that's in your vocabulary, in your dictionary. No, Grammarly will also check the content and context of your sentences, of your paragraphs. So it will give you feedback on how your writing is. Can you convey your message? Is it clear? And will make suggestions on how to rearranging sentences, how to rewording stuff in order to make it more clear. And if you look at the quality of these autocorrection tools nowadays, they have really improved significantly, and they're, very close to human level performance, and of course much quicker. However, I don't want to talk too much about generative AI in other domains. What I would like to brainstorm with you a bit is how can we translate these technologies from other domains to our domain, to process engineering. So what I would like to propose today is a vision of how to use generative AI in process engineering. And the first example is how can we think about a tool that is doing autocompletion for process engineers. And well, what we propose is exactly that. So we propose a new model that is auto-completing chemical process flow sheets. So the idea is that you as a human engineer, you start to develop your process here, for example, in Aspen Plus, and then the software will automatically suggest the new topology, new unit operations, as well as operating points, design points, and so on. So really a tool to accelerate development. So next question is, what would machine translation be in our domain? And this is a bit more tricky because as engineers, we work with P&IDs, PFDs, with engineering diagrams. We don't work too much with different languages here. However, what we propose is to cast the development process of P&IDs, so piping instrumentation diagrams of chemical processes, as a translation problem. So the idea is to understand that, let's say, in early development phase of a chemical process, for example, represented as a process flow diagram, PFD, we can cast as one language, and then we can say, hey, a P&ID, a piping instrumentation diagram, we can understand as a different language. And by thinking about this as being a translation problem, translating a PFD to a P&ID, we can basically develop a generative AI algorithm that is helping us to do this translation for us or with us. This way, we can train generative AI algorithms to develop P&IDs. And the third counterpart is relatively obvious now, probably. So what we do is we envision an algorithm that is automatically correcting engineering documents like P&IDs. And it's not only about finding the obvious errors, it's also about analyzing the context, and it's also about giving a reason why this might be an error, and then giving the human the possibility to check that, confirm that, and so on. For example, here, a controller is missing, so you as a human can check that, you can add the missing equipment, or you can say, I want to ignore the suggestion. So these are the three generative AI applications I want to go through today in my talk. But the big question is, if we have this idea, if we have this vision, what does it take to actually develop it, to implement generative AI? And if you look at what is happening in the literature, in other domains, is usually generative AI is based on some combination of big data, information representation, and model architecture. And people used to add computing power here. I don't add that here because that's now given essentially, at least for our problem sizes. So if we look at one example, ChatGPT here, what we see is, yes, ChatGPT indeed is based on big data, several terabytes of data. It is indeed representing information in a meaningful way. In that sense here, it's text. And ChatGPT has really accelerated, or has been possible essentially due to specific machine learning architecture, which is a transformer architecture. So the questions I would like to answer today in my talk is essentially, if we want to develop such an application in process engineering, do we have big data? How do we get it? How do we represent our information in a meaningful way? What model architectures do we need? And if you think about it, there's also one point that is differentiating us as the chemical engineering domain from other domains, which is we have mechanistic knowledge. So there's an additional question, which is, how can we utilize this existing knowledge, and how can we integrate that into our generative AI applications? Because this knowledge is usually not existing, or not existing in a structured way for existing applications like ChatGPT. So what I do now in my talk is I will basically go through each of these sections one by one, starting with the big data. So data is kind of the fuel, the resource for machine learning algorithms, right? So the question is, if we need such big data in order to train meaningful machine learning algorithms, do we have it? Is chemical engineering actually a big data domain? And if you read recent literature about that, for example, this article here, The Promise of AI in Chemical Engineering, is it here finally? The answer is no. The answer is usually our domain is not a true big data domain. Why? Because we have limited data. However, most people argue that instead what we have is we have the mechanistic understanding, and we can use that in order to compensate for our lack of data. And I do agree with this. I agree that we have limited data. It's not as easy as with scraping text from homepages or so. And I also agree that we need and we should use our mechanistic knowledge. However, I also feel that in our domain, people are not using the existing data appropriately. So I believe we have quite a bit of data, and you as engineers, as scientists, you process all of this data on a daily basis. So I'm sure you already sent a few emails that are somehow relevant to chemical engineering, maybe today, maybe this week. Some of you may work in a lab, so there's lab notebooks. There's tons of property data. There's molecular simulations. Very relevant for our application, there's chemical process flowsheets, P&IDs. There is process simulations, maybe in Aspen, maybe in other software. There's CFD simulations. There's a lot of publications that can be scientific, that need patents. There's a lot of internal documents. There's HAZOP studies. So there is a lot of data. The question is, why do people still say that we are not a big data domain? I believe the main issue is that our data, it's heterogeneous. It's in different formats. It's saved on different places. It's not easily findable. And very importantly, it's not machine readable. And if you look at the machine learning community, they have been relying on a lot of data that is available in the structured format, in CSV files, for example. And we don't necessarily have that for all of our relevant data. So our data is a lot more complex. And in my talk today, you saw that already. The examples that I mentioned are around process development. So what I would like to focus on today is one type of data, which is chemical process flow sheets. Why am I highlighting that? Because chemical flow sheets have a lot of information relevant for process engineering. And these flow sheets are usually either in company reports, in the commercial domain, so PDF documents essentially, and in the public domain, these are usually in books, scientific publications, and patents. And we work with both. We work with the information in the public domain as well as with the information in the commercial domain. Today, I will focus a bit more on the public domain to just show you how we can actually get this data in order to train our machine learning algorithms, for one example. So the task is essentially, how can I get all this unstructured flowsheet information from publications, from books, from patents, and structure that in order to make it machine readable and then usable for our machine learning algorithms. So what we work on is something that we call flowsheet mining, and the process is as follows. So we start on the left-hand side with a list of relevant journals or ISSNs. And having this list, what we can do is we can use APIs, so application interfaces of the publishers, in order to download all the PDF documents of the corresponding publications and patents. So by doing this, we can essentially mine the internet and extract all chemical engineering publications ever published. So this gives us a pile of millions of PDF documents. However, what we are interested in at the moment is essentially the chemical process flow sheets. And these flow sheets are usually images. So what we do is we extract the images. And that's a relatively straightforward task because they're embedded in the PDF documents. So it's relatively easy to automatically cut them out. And then this gives us a whole lot of different images, so millions of different images. And only a very tiny fraction of those are actually relevant for our application here. So only a few of them are showing us the topology of a chemical process flow sheet. So what we did is we trained an image classifier. So this is itself a machine learning model. And that's a standard example that many people will show you if they talk about machine learning. You have an image of a cat, you have another image of a dog, you show the machine learning algorithm the image, and the algorithm will tell you whether the given image is a cat or a dog. So here what we did is we basically trained an algorithm to detect flow sheets. So you give it an image, it will tell you, hey, this image is a flow sheet or it's not a flow sheet. So from machine learning technology, this is very established already. It's relatively easy to set up and it just works. And we are running these algorithms at the moment on our servers. So what we have so far is we have publications from around 5 publishers, 230 journals. We have already over 2 million publications by now and a few thousand flow sheets that we extract. So what we get in this way is we get a structured or a way to identify flow sheets in literature and patents. However, what you need to recognize is these are still not machine readable. Why? Because these are just images. So we don't have the topology of the flow sheet in a machine readable format. And this is an issue that you have also in industry, right? So there is a lot of P&IDs, there's a lot of PFDs in industry, and they might be at one point, so they're findable. However, they're still not machine readable. Why? Because it's it's made for human communication, right? Process flow diagrams, P&IDs, are made to communicate information between different engineers. It's not made for communication between software necessarily. So what we developed very recently is the software called Digico, Digitization Companion. So what we do here is basically we have a software where you can read in an image of a P&ID or PFD. And then our software is connected to a number of machine learning algorithms that we developed. And these include algorithms for object detection. So this is a computer vision algorithm that is able to detect over 500 different objects or symbols on a P&ID, with algorithms to detect the connectivity between these symbols. So combining those objects and the connectivity, what we can do is we can basically translate the given image into a process graph. So we can extract the topology information. We have algorithms to detect the text and contextualize it. So read in piping text, for example, as well as table extraction and information extraction from the title blocks. So by putting all of this together, running our models, we can essentially extract all the necessary information from paper P&IDs, from PDFs, from scans, and so on. And we can translate that into smart P&IDs in different formats. For example, DEXP, which is the data exchange standard for the process industry. So one standard format for representing flowsheet or P&ID information. So by doing this, like in the public domain, the data mining, or in the commercial domain, collecting all the information at a company and then digitizing that, what we get is we can get this big data, the digital flow sheets that are needed in order to develop generative AI on the process flow sheets. And the next step is the information representation. So the question is here, how can we represent the information that we have, the flow sheet information, in a way such that a machine learning algorithm can actually work with that? And if you think about that, that's not a trivial problem, because for a very long time, what people used to do is they used to train machine learning algorithms only on scalar or vector inputs, right? It was always mapping a number to another number or vector to another number. So that's a classical regression problem. And in the chemical engineering domain, this is the kind of machine learning that is very commonly used. However, now that we want to represent a flow sheet as an input to a machine learning algorithm or as an output to a machine learning algorithm, stuff gets a bit more challenging, right? So we need to think about how can we represent our information in a way that machine learning algorithms can deal with that. And one relatively obvious way to do this is a flow sheet graph. And that can be as simple as, just representing each part here, each unit operation of a flow sheet as a node, right? And then putting that together, and we get some kind of directed graph representation of the flow sheet. And then if you want to add additional information, so for example, the type of unit operation, the concentrations, the design specs of the units, and so on, what you can do is you can add a vector to each of these nodes. We call that additional feature vectors, and thereby you can basically represent all the necessary information. And that's the simplest example of a flowsheet graph. What you can do as well is you can add additional information. You can use different graph concepts. So for example, you can encode this information in hypergraphs, in knowledge graphs. You can use advanced data models like DEXP or AutoCAPE for this, and then add more information and more complexity to the graphs. But the general concept is you can represent flow sheets as graphs. There's another alternative here which I would like to highlight, which is you can also represent flow sheets as strings, as text. So how does that work? So this is an idea that is inspired from smile strings. So many of you will probably know smile strings already. Smile strings our way to represent molecular structures, which are also graphs usually, as strings. And we did the same for flowsheet information. So this work is basically built on top of a framework that was developed by Professor Zahinides from CMU. We extended that recently, and basically it gives you a way to represent flowsheet information as a string. Currently, this is still limited to topology information. Why am I highlighting this? Well, many of the generative AI algorithms are actually based on string inputs and string outputs. Why? Because they are based on human language. So by representing a flowsheet as a string, we can basically use out of the box a lot of existing machine learning technologies already. So without big changes, without a lot of work, we can just plug them in, train them, and use them for our domain. So that's why I highlight these strings here. However, in the long term, it is a bit more sensible to use the graph representation because it's easier to include additional information here. So I already hinted at a bit. If we think about information representation, that always goes together with the model architecture, because the model architecture depends on the information and the way it's represented, essentially. If we think about generative AI, most of the algorithms are somehow related to this transformer architecture and the attention mechanism. So this is also technology somehow used in applications like ChatGPT. However, there's also a lot of other modern generative AI methods, which are based on generative adversarial networks, variational autoencoders, diffusion models, flow-based models. There's a lot of opportunities here. What I would like to highlight is basically the conceptual difference between the standard transformer architectures and the graph neural networks. Because essentially they link to the different representations that I introduced earlier on. So if you have your flow sheets or your information represented as text or strings, this goes naturally very nicely with the transformer architecture. If you represent your information as a graph, you somehow need something like a graph neural network in order to present to process your information. So these graph neural networks have been used in chemical engineering already quite a bit, mostly for molecular graphs and molecular property prediction. However, we have recently also developed a graph neural network for process graphs, so where we can, learn from process graph structures, learn how to synthesize new processes. However, that will not be the focus of my talk today. So if you're interested in that, check out our paper. Today, what we do is all the models that I show you are essentially using this S files, the string notation of flow sheets, and they also use some kind of transformer architecture. So they all work on text essentially. So what I would like to do now is I would like to go through the 3 case studies one by one and show you our first results or first demos essentially. The first one was the autocompletion of flow sheets. So what we did here is first we started with a data set, and in particular we had a data set available, or we got a data set of around 200 real chemical flow sheets. Where did we get them from? Well, these are actually results of process simulation files. So we extracted topology information from process simulation files. And in addition to that, what we did is we generated 8,000 synthetic flow sheets. So basically, we developed an algorithm to automatically develop flow sheets, synthetic flow sheets that are not real flow sheets, but similar to real flow sheets. And we use that in order to generate synthetic data. And our models have a vocabulary size of around 50, which means that we have around 50 different types of unit operations in our data. And what we did is we used a model, a GPT-2 model, which is a decoder-only model architecture, which is basically an out-of-the-box generative AI algorithm with a lot of parameters. So we have over 80 million of parameters. And what we did is, as an input to this model, we put the incomplete process flow diagram. And as an output of the model, so the goal of the model is to predict the next unit operation. And what we could do now is we can, run the model multiple times, one after another, predict the next unit operation, the next one, until we have completed the flow sheet. Now what you see if we train these models, first only on the real data and then on the synthetic and the real data, we see that this real data, the synthetic data is really helping the model to learn something meaningful. So this perplexity value is decreasing quite a bit. So what is perplexity? Perplexity basically quantifies how close a predicted sequence or predicted flow sheet in our case is to the real flow sheet. So the lower the value, the better. So the pre-training helps actually quite a bit. And let's make one example here. So if we start to put together this flow sheet here, the model would make this suggestion, for example. So if you look at this, what you recognize is, first of all, it looks like a real flow sheet. So this, looks familiar, doesn't look like complete bullshit. However, if you go a bit into detail, what you recognize is it doesn't make complete sense. So for example, you could recover a solvent here. So what you need to understand is this is a proof of concept. It's our first development in this area. It's the first paper in this area. And there are a number of limitations. And the first and most important one is the algorithm is currently limited to the topology information. So we don't know what we want to produce in this process yet. We only know what you see here on the screen, right? So you don't know what is a product, so therefore you can't really know what's the best way to separate it. You don't know the concentrations, you don't know the throughput, you don't know the quality requirement or the constraints. So at the moment, what the model is really doing, it's recognizing patterns in the topology of flow sheets. However, on the bright side, what we recognize is, hey, it's working. We come up with reasonable patterns. So we can learn from flowsheet structures. So adding more information to the model is just a matter of, putting the information in the right format, adding the model architecture, retraining the models, and further developing that. Syntaxing application that I have is this PFD to P&ID translation. So how can we learn the industry, the translation process? What we do here is, again, we generate a lot of synthetic data. Now even more data, so 100,000 synthetic flow sheets and 250 real flow sheets we have here, or here P&IDs, flow sheets with control structure. We took a slightly smaller model, a T5 architecture, which is also a standard transformer architecture, essentially. And here the input of the model is the process flow diagram, and the output of the model is a process flow diagram with the control loops. So we don't go all the way to P&ID yet. It's really just predicting control loops and the control valves. So let's take a look at an example. So this one here is a prediction of the model. So what you see in black is essentially the input to the model, and in black with blue, we see the output of the model. So the model is predicting the location of the control loops, as well as the valves, as well as the type of the controls, right? And again, if you look at it, it looks reasonable. Many of these control architectures actually make sense. If you go into more detail, you will recognize, well, it's not perfect yet, and it suffers from more or less the same limitations as the previous work. So at the moment, we only see the topology of the flow sheet. For example, we don't know if the product will be at the top or the bottom of the distillation column, which would have an impact on optimal control strategy here. However, we see that in general, machine learning algorithms can learn from flowsheets. In general, machine learning algorithms can make predictions for complete flowsheets with control architectures. So I believe this is an important and first step towards automating the engineering process and helping the engineers to develop P&IDs quicker. So now you might say like, hey, 100,000 flowsheets, that's a lot of data. Do we have that? Do we need that? So we did a small study where we decreased the data amount in order to check the performance. So with around 100,000 flowsheets, we have a top 5 accuracy of around 80%. If you reduce that to 10,000 flowsheets, we have an accuracy of around 65% at the moment. And with around 1,000 flowsheets, we are at around 0% accuracy. So, given these first results, what we recognize is, hell, we need a lot of data. We need probably around 10,000 flowsheets in order to make this work. However, on the bright side, this is just the first step. I'm sure we can reduce the data demand significantly in the future by, for example, including more mechanistic knowledge, but also making our machine learning models more efficient in training. And then the last application, the autocorrection of P&IDs. Here again, we generated synthetic data. And we have the same vocab size, so also around 50 different unit iterations. We also use a T5 architecture again, so standard transformer architecture, more or less out of the box. The input of our model are process flow diagrams with errors, and the output are corrected process flow diagrams. What you recognize here is now we don't have real data anymore. Why not? Because, well, what you need is you need annotated PFD data. So you need, wrong PFDs and corrected PFDs. We did not have that, and we did not want to spend the time to develop a huge data set here. This is more like a proof of concept. And what we recognize is essentially that we have a relatively high accuracy of around 80%. And I brought an example here as well. So this is an example of one of the synthetically generated P&IDs. So what you recognize is the P&IDs are put together based on rules, essentially. So we draw random patterns from P&IDs, put them together. So this one doesn't make necessarily sense. It doesn't produce a real product, but it serves as an example for training of the algorithm. And what you recognize is if you run the algorithm on this synthetic P&ID, the algorithm will detect 2 errors. The first one is down here. So basically the algorithm says, well, there is a recycle here, right? And there will be a pressure loss. So you better add a pump here. So this is something that, makes sense. That's probably an error you would also spot if you look at the P&ID for some time. There's another error that this algorithm is spotting, which is, hey, the flow, you should please control over this motor here, or the compressor, and not using the valve here. Does this make sense? Is that correct or not? Well, we don't really know. We can't really say, because in reality, this will depend pretty much on the context of your P&ID. So it's not a clear error, but still, could be a valuable suggestion by the algorithm. So again, this is very much proof of concept stage, but I believe if you think about it, if we are able to deploy that on real P&IDs on a large scale, there's a big business value behind it, and there's also a big gain in safety here, because if we are able to detect errors earlier, then we can save a lot of money and potentially also reduce the risk in operation later on. So what I did is I essentially showed you 3 different applications of generative AI, right? The autocompletion of flowsheets, PFDs to P&IDs, and autocorrection of P&IDs. So what I would like to emphasize is, while these are 3 different applications at the moment, we want to put that together essentially. So, and this is inspired a bit by a talk that you have probably seen, maybe in 2007 even. So I will just bring a small sequence here. I'm not sure if you can hear the sound as well.
Oh no, because we didn't preload it, I don't think.
So basically, you see Steve Jobs emphasizing his innovation of an iPhone in 2007. And there, the real innovation was not necessarily the individual functions, but was to put everything together, right? And that's what we work on at the moment. So we work on Pilot, which is a process intelligence learning and optimization toolbox. And the idea is really that, a bit like, you know, foundational models that you see in text now more and more, that we want to develop a foundational model for the process industry, where we combine all of these different applications and much more into one big model that is assisting process engineers in the future. And this model is integrating not only flowsheet information, but also different modalities of data. So we call that multi-model learning usually. So we are developing an AI algorithm that is integrating P&IDs, but also the actual sensor data, as well as property data, in particular a lot of information from reports, helping us to develop more efficient HAZOPs, and so on. And these algorithms are also able to simulate themselves, so execute simulations themselves, get the results, use these results in order to answer questions to the engineers. And of course, with these kind of models, you're also able to, you know, communicate in natural language, for example. So with that, I'd like to conclude my talk. So what I showed you is that the digital engineering data is key for future AI applications. So without the data, well, we can't do a lot. I believe I showed you that machine learning algorithms can learn from flow sheets. So this is a big breakthrough for my research, because we see the proof of concepts work, and therefore we can, you know, start to think about bigger next steps as well. The data size matters, so the more data we have, the better. And here I'm looking in particular at the people from industry, thinking about models, how we can share data in order to make these models more powerful. And in my personal opinion, well, AI has a big potential to transform chemical process industry. And for those of you who were paying a lot of attention in the very beginning, you might be wondering that I forgot something, which is I promised you to also talk about the mechanistic knowledge, right? And I suggested that we should include that in our machine learning algorithms, but then in the application that I showed you, there was no mechanistic knowledge. There was just a lot of data, right? So the question is, should we include that knowledge or not? And if yes, how? So why didn't I show it here? And the simple reason is because I didn't get there yet. So I'm a strong believer in mechanistic knowledge. I'm a strong believer that we should include that and use that for our machine learning algorithms. But all of the topics here are still in the early research phase. So there's still a lot of scientific challenges that we need to overcome. And one of them is to include the mechanistic knowledge. But let me emphasize three of the main challenges. First one is, at the moment, we're ignoring all the knowledge. In the future, we need to leverage that. And that could be by including physical equations or rules in our machine learning algorithms. The current approaches are solely considering the process topology. And there's a fix to that, which is leverage more additional information. That could be DEXB information, that could be additional stream data, equipment data, simulation data. So you can add all of those to the machine learning models with a sensible data representation. That could be knowledge graphs, for example, and then you can learn from this as well. Of course, AI is very data hungry, but we have some kind of lack of data. So we need to develop new techniques in order to reduce the data demand. That might be data augmentation, that might be synthetic data generation, but we also need to collaborate more on this. We need to think about ways how we can share data in a way that the confidential data still stays confidential, but we can still, leverage the data of multiple companies, for example, for joint models. And with that, I'd like to thank very much my team, because most of the work I showed you here is not my own work. It's a teamwork, essentially, of the Process Intelligence Research team here in Delft, and also of a lot of master students that, I can't, there's too many, I can't name all of them now, but I would like to thank all of them. And I would like to thank all of you for your time and attention, and I'm happy to answer your questions. Thank you very much.